Is everybody excited? I'm just going to start with that. That's good because I can guarantee you, you have never seen the Milky Way like you're about to see it tonight. And it's in part, that was a scream, I like it. Whatever this energy is, I'm going to work with it. What you're going to see is rendering of data that we do here at the American Museum of Natural History. And I'm so excited to show it to you because, you guys are going to be some of the first people to see data in this way, rendered in this kind of way, because you are here in this place at the American Museum of Natural History where we have some of the best data visualization tools. To start, I want to set the landscape for you, the landscape of astronomy. This is a picture of the nighttime sky, as it's about the best kind of nighttime sky anybody on this earth could hope to see. This is a picture of the nighttime sky. I was actually inside of one of those telescopes when this picture was taken. This is a picture taken from the Las Campanas Observatory, which is in northern Chile. And you're seeing a fairly realistic, it's just a little bit heightened, beautified image of what the nighttime sky should really look like. This is actually a very special picture. This was actually on my birthday a couple years ago. The photographer, Yuri Beletsky, took it for me while I was observing. Notice there's this red dot on the upper right-hand side. I don't know if you guys can notice that. It was a total lunar eclipse this night. On the left-hand side, you're seeing the large and small Magellanic Clouds. So you can tell it's the southern hemisphere if you're seeing those two satellite galaxies of the Milky Way. And this picture, to me, I've got a giant version of this up in my office. It's one of my favorite pictures taken. And it is a gorgeous view. This is the view of the nighttime sky. And so when I ask all of you what you think of when you think of the cosmos, you probably think of the nighttime sky. And you'd probably want to think of the nighttime sky that I've got pictured for you here. However, and this is a beautiful image, you're missing some critical information here. The critical information that humans are just not capable of detecting is how far away all this stuff is. Your eyes can't tell that. You can't tell that those two galaxies are galaxies, that they're not inside of the Milky Way that we live in. You can't tell that. You can't tell what in this picture is the closest star to you. You can't see that. You actually need something else. You need science, which is real, not fake news. It's real news. I'm gonna just go with the applause on that. Science will give you answers to things like how far away is a star, and we've figured that out. The other thing that you don't get from this image, while magical and beautiful, is you can't see motion in this image. All of these stars, everything that's in this picture right now, this snapshot taken on a gorgeous night during a total lunar eclipse in Chile, is moving, but you're not seeing it here. And what I get to show you tonight, through the magic of data visualization tools and the magic of science, but it's not magic because it's science, I'm going to show you how stars move. I'm going to take time and I'm going to turn it on for you, and I'm going to show you how we can learn a tremendous amount about our galaxy by looking at how far away stars are and how they move. So I've got several movies that will take us through that. And the reason why I can do this tonight, and I'm sure many of you actually don't know this because it didn't get the kind of press I think it should have. That's a satellite called Gaia. Gaia was launched several years ago, and on April 25th of this year, the entire perception of the Milky Way was changed. The entire perception of astronomy was changed on April 25th of this year. And the foundation of astrophysics, the foundation of everything you know about the cosmos, you need to know how far away something is. You need to know how far away a star is. It's the foundation of stellar astrophysics, it's the foundation of cosmology, it's the foundation of everything. And everything we knew until April 25th, 2018 of this year, was based on a prior mission called Hipparcos. There were 120,000 stars that Hipparcos had measured distances from. And then we extrapolated on that and got a ton of new information. Gaia came out on April 25th and released 1.7 billion distances to stars and motions. 120,000 is what modern astrophysics was based upon. 1.7 billion is what we got on April 25th. So that's a big difference. You can applaud Gaia because it is an amazing mission. So what I'm going to do for you is I'm taking subsets of that Gaia data. Anytime you want to see Gaia, come to something we do upstairs in the dome. I can fly you through 900 million stars. No one on this planet has seen that unless you've seen it here, just FYI. But I'm going to take the Gaia data set, I'm going to break it down into subsets, and I'm going to explain to you how science has moved forward using this amazing data set with data visualization tools. So I'm going to start with, I just showed you the Milky Way, and this is going to be a movie that I made using PartyView software. It's an open source piece of software, and this is a subset, so 1.7 billion stars breaks a laptop. So just in case you were wondering, it's very hard to render that on your laptop. So I'm going to show you subsets. So this is going to be a couple 100,000 stars, a couple 100,000. It's like me rolling my eyes at that. That's amazing. A couple 100,000 stars. I'm going to run through this. So this is not an image. These are all dots. These are all stars for which we've measured the positions. And already you can see, before I start the movie, it looks like the Milky Way already. I call this pointillism. It's pointillism of the Milky Way galaxy. No one has ever been able to do this before. I'm going to turn this on, and you're going to see this is me flying around in the data. It's a screenshot of me using the software. And so the best part of this now is I can fly out. I can actually move outside of the data. This is a specific subset of data. These are the hottest stars. So we never knew exactly how far away they were because no one could actually measure their distances before. We didn't actually have a satellite that could do it. You can see I'm rendering this. I'm moving out. So these are what are called the O and the B stars that live hard, die fast. There's like that's literally what happens. They are very big, and they die in just a couple million years. So they never move outside of the plane of the Milky Way. So as I fly out, the dots that I turned on there is the locations of what's called star formation regions. Most people know Orion, right? Everybody loves Orion. Orion is the closest star-forming region to the Earth. And so as I've pulled out, part of why I think this is phenomenal, notice these streaks. I kind of call them fingers of God. And those are marking for you clumps. These are where star-forming regions are located. And I'm going to run it again. And as you fall out, what you'll see is, okay, we all know, that image of the galaxy you just saw, we didn't take that picture. Voyager is kind of the farthest thing we ever sent, and it's barely left the solar system. So we've never taken a picture of the galaxy. But what we're able to do in this map, and as I fly out here the second time, what you'll see is the locations of those star-forming regions, those locations of these hot O and B stars are telling you the shape of the Milky Way galaxy. It's been heavily debated what the shape of the Milky Way galaxy is. Does it have spiral arms? I mean, we think so. We're in a spiral galaxy. What do those spiral arms look like? You can now use these stars as a map to try and get to that structure. And part of why, at this point in the video, that I'm sort of zooming around, and you'll see I turn on this image of the galaxy and turn it off. As you blink on and blink off, what you're seeing is gaps and non-gaps, which look like you're basically getting the structure of the spiral galaxy out from this very simple thing of just mapping the hottest stars in the galaxy. Okay, next video I'm going to show you, and this is my favorite one. You're not supposed to have favorites, but I have favorites. So this is my favorite one. This is what I call the solar neighborhood flybys. This is something that I've wanted to do, and it's just something I've always wanted to do. If you know how stars are moving, and if you know how far away they are, you can look at their trajectories. We are stuck in this static view, like I mentioned, of what the galaxy looks like right now, what the nearby stars look like right now. But once Gaia showed up with all of these motions and distances, we can turn time on, and you can see, are these the stars that have always been the closest stars to us? Did we ever have a flyby? Did another star come sweeping through our solar system and knock a bunch of stuff around, kicking comets and asteroids from the Kuiper belt and the Oort cloud, the asteroid belt, in towards the inner solar system? Well, we can turn time on this video. So this is a cartoon version of the sun. This is rendered with software we have here called OpenSpace. So again, in the corner here, it's telling you what software I'm rendering this with. And these are all stars that you cannot see with your eye, because your eye can't really detect anything but the brightest stars. And so I'm going to turn time on right now, and it's going to go over a couple million years. So you're going to watch your future. And don't be scared, but kind of be scared. So there's a lot of stuff going on here. So what you're seeing, again, don't be scared, but be scared, that all of the stars around you are moving. Everything is moving. And you don't know, though, are they moving towards you? Are they moving away from you? What this video is showing is mostly the stars' motion through the galaxy. So you're watching the stars have their trajectory in the plane of the galaxy. But notice some of them are flying closer than others. And what was an immediate thing that came out of this is actually something that we knew from Hipparcos, but we know it so much better now, is that this is another little movie that I'll show you a close-in. In 1.2 million years, there's a star called Gliese 710. It's about 60% the mass of the sun, and it's going to come within the Oort cloud, which is that cloud of debris that I'm flying you towards right now. You can see the star right there. You can come in past the glare of the sun, past the Kuiper belt, into the Earth, and in 1.2 million years, look out, who knows if we'll still be around, but if we are, Gliese 710 is doing a flyby. When it does, it looks like it'll kick around a bunch of stuff in the Oort cloud. When it does that, it sends stuff into the inner solar system. Now, okay, I'm not trying to scare you, but that is an absolutely important aspect of understanding solar systems, to know what is the dynamic nature of how things move. And just one other thing on this, too. I'm going to run this again. How many people have heard of Oumuamua? Anybody hear of Oumuamua? A couple of shouts, one or two. Oumuamua is this object that was a recent visitor. So I'm just going to turn this on to continually scare you. Oumuamua is this piece of debris, it looks like, that came from a different solar system. It flew through our solar system very recently. It was discovered a year ago, and we caught it. It's on what's called a hyperbolic orbit, which means it's not bound to our own sun. Flew right out. Now, using the data like this, astronomers, it was just last week, used this exact thing that I'm showing you to trace back where Oumuamua might have come from. Now, we're not sure that it's right. I mean, that's also the other aspect of this. We're not positive we've got all of the velocities and the positions correct, but never before in time have we been able to even take the step towards this, where you could trace back the motion of an object that came from a completely different solar system and try and find its host, to find where it came from, an ejected piece of garbage from some other star that just passed through here. And we studied it. And now we used this kind of thing to trace back where it might have come from. So that should excite you, as that is the science on the horizon of what we're able to do in the nearby solar neighborhood. Another thing that we can do with this gigantic data set, this is something that I work on heavily, is look for objects that move together. It's kind of like looking for family members of stars. Until you know how far away they are and how they move, you cannot know if they're moving with each other or not. So what this movie is rendering for you, this is a catalog of about 10,000 stars that I'm isolating for you. They're very near to the sun. And I'm going to turn time on here, and every one of these objects is moving with something else. So you're going to watch, and this is over millions and millions of years. So the beauty of this is that you will never get to see this because we don't live long enough. But I can simulate it for you. And so now as you watch these dots, notice how they're moving in clumps. So you've caught a chunk of things over here on the far left-hand side. Everybody's got a partner here. And this is how you figure out where do stars come from? How do stars evolve? How do they end up interacting with each other? Do they stay together? Are these clumps of just 4 and 5 stars, because some of these are clumps of 4 and 5 stars that we've only recently discovered, are they the last bits of the core of a giant region of stars that had formed together millions of years ago, billions of years ago? This is the kind of stuff we get to figure out now. It's like forensic evidence that we didn't have before, and all of a sudden we have access to. This is another one. This is now a catalog. That was 10,000 stars that I was focused on because they were all co-moving with each other. This now is a collection of stars that are all young. So we know that they're young. All of these show the telltale signatures of an object that is a young object. And so I'm going to pull out a little bit, and you're going to see there's about 10,000 stars in here. And this I work on nonstop because the young stars near the sun are also where you would look for the baby solar systems, for the newly forming planets, for the areas where you're going to get a glimpse at maybe what our solar system looked like back when it was just a little baby. And as you pull out here, this is where it gets intense, because you're seeing what's called the Centaurus lupus super complex. I mean, as I'm saying that, I'm forgetting the full jargon for it. But this is a gigantic complex of young stars near the sun. And I'm going to turn time on in the last moment, and you'll watch that these objects, so these are the labels of some of them. There's Coma Berenices, there's Pleiades 8, there's the Hyades and the Pleiades, which many of you might recognize because you've seen it in the sky. And now time is turned on, and you're seeing how these things move. So they move together, but do they move together forever? That last video I showed you might be the last remnants, the cores of these things, which at this point we know are co-moving with each other. They're all young stars, and this is where the solar systems are forming. This is where astronomers look. And Gaia just gave us this unprecedented look at where they came from, because you can actually run time backwards and forwards and see how they interact with each other. One other thing that Gaia doesn't do that great of a job with, yet I was still able to pull out info, and I have to say this because this is my passion and my science, which is brown dwarfs. This is a video that's showing you, even there's stuff that you can't even see with your eyes in the Milky Way, yet is right there. So brown dwarfs are these objects in between stars and planets that are everywhere. And I just wanted to promote for you as well that mapping the Milky Way and mapping the solar neighborhood is something that we're still doing today. The third and fourth closest star systems to the sun were only discovered in 2013 and 2014. Just imagine discovering an object that's sitting there right outside. It's like turning over in bed and somebody's there. And you're like, when did you get there? Like, how did that happen? But that's still happening. They're really cold, so it's also like you can hide out because they're cold. And I run a citizen science project called Backyard Worlds, backyardworlds.org. If you're interested, go to the website. help discover new worlds. Gaia isn't as good with these because they're a bit too faint. Now I'm going to reflect on exoplanets. And this is a movie that we've rendered here using UniView software to give you a highlight of the current view of planets around other stars. So this is a flight off of the surface of the Earth into the nearby solar neighborhood, out of the glare of the solar system. And what you're going to see is, as we move out of our solar system, a bunch of stars are going to come up that we've only discovered since basically the year 1995. Since 1995, we've been discovering exoplanets. And now all of the blue circles are showing you where stars near the sun have been found to have an exoplanet around them. The majority of these that you're seeing, you can see that they're all around you. And as we pull out, what you're going to see is a special catalog of objects. It's going to be color-coded in yellow, and it's called the Kepler Planetary Objects. Kepler was this spacecraft launched many years ago. So here comes Kepler into this field of view. Notice the blue circles here, which are marking for you the locations of planets around stars, is very close to the sun. And that's because a lot of those were just looking at the brightest stars using a technique called the radial velocity method. Kepler used what's called the transiting method, which means you stared at a field of view and you watched and waited for a planet to cross in front of the star from your point of view. And so this is going to fly outside of the Milky Way. Again, we didn't take this picture of the Milky Way because we've only gone as far as maybe outside the solar system. So this is an image of another galaxy that we think looks like our own. And this should both absolutely amaze you and also make you wonder, oh my goodness, there's a lot more to the galaxy for us to try and figure out. So these objects, as we pull out, you can see where Kepler was. This was our rendered view of it prior to Gaia. I'm going to show you the view from Gaia, and part of that is Kepler redefined how we knew about exoplanets. Like I said, those exoplanets that you saw with the blue circles, those were fairly close by. And while we had a lot of them, we didn't quite have them the way that we do with Kepler. You can see that you can go way further out, way towards the edge of what you can do in the galaxy. And there are now thousands of exoplanets that have been discovered via Kepler. This is showing it to you now all mapped properly with their distances from Gaia. And I'm going to turn time on in just a minute. And what you're going to see is Kepler break apart. So this is the Kepler field of view. This is the view that you would have gotten from Earth, from the detectors. And what you want to look for is once you have them all mapped out, you want to be able to see where they're going and where they came from. So as we're close in, you'll see the detector field of view comes in, and we turn time on. And you're going to watch where these stars came from and where they're going. That kind of broke the internet when we put this on Twitter the day after Gaia came out. So you're watching where those stars came, where are they going, who are they moving with? This is the history of these exoplanets. And this final thing that I'm going to show you is the thing that we can now do with Gaia, matching it with very complicated missions that now color code all of these objects by their chemistry. So you can take very complicated surveys that go and measure the abundances of different molecules, and you can actually see, this is showing you in color-coded how much iron you're getting out of stars, how much iron you were getting in Kepler, and then lots of other field of view. And notice there's the green, and then it gradients out to the blue. Blue means low metallicity. It means that there's not a lot of metal in that. That's a signature of older stars, which is what you see when you get outside of the galaxy. One more view of that from this perspective. And by the way, the reason why this looks so funny with these footprints, these singular footprints, is because that's the view that we had from the telescope when you looked up and you took an image of the sky. It's in 2 dimensions, and through the magic of data visualization, we can actually fly you through those data sets with Gaia parallaxes and beyond. All right, so that's your quick tour of all of the exciting aspects. I have probably 100 more movies I could show you, but I'm out of time on the movies, so I'm going to leave you with this takeaway. The Milky Way galaxy, via Gaia, via many surveys on top of Gaia, is being mapped like never before. And this data is revealing just the intricate details of where stars come from and where they're going. And if you're interested in playing with the data, this is not just for astronomers. This is for the public. This is for everybody. This is for the kids. You guys are right here. I'm pointing at you. This is for everybody to play with. So download our software, download the data, play with it. It's 1.7 billion stars. That's too many for the astronomers. There's not enough astronomers for all of the data. So please consider this your invitation to the party of mapping the galaxy.